Hi, everyone, and welcome to the first of the parallel sessions. My name is Carsten Baum, and I'll be chairing this session on computational multi-party computation. We have three very interesting talks ahead of us, and so I already want to give the stage to the first speaker, so we don't waste time. And that's Mark Ravinius, who will be talking about MPC with publicly identifiable abort from pseudo-randomness and homomorphic encryption.
Okay, yeah, thanks for the introduction. Somehow the first slide is missing, but yeah, so I'm going to talk about my paper, multi-party computation with publicly identifiable abort from pseudo-randomness and homomorphic encryption. So it's the first talk in the MPC track, so I shortly recap what multi-party computation is. As the name suggests, there are multiple parties, multiple people, multiple companies, something like that, and they want to compute a function together. As one example, you could think maybe they want to evaluate a machine learning model together. One party has the model input, and the other party has the model parameters. Can be also more complex. Maybe they want to outsource the computation because they don't have the compute power to do this themselves. And maybe the data is somehow distributed in an even more complex way, like multiple distinct people have the inputs, for example. Then we talk here about security. So in the most basic model, we have a semi-honest adversary that tries to attack the model. So they can see the state at certain corrupted parties and also all the messages across the network. And harder would be a malicious adversary. They control some of the corrupted parties and they can do arbitrary things, trying to change the result or maybe learn more information. And still, the protocol should be secure in these cases. So what that means is, on one hand, the inputs of the honest parties should still be kept secret, private. And on the other hand, we want the correct result. Otherwise, the computation is not useful. Or in some cases, we cannot do that, and then we want to abort and find out that we couldn't do the correct result. So what happens if we have these strong malicious adversaries? They do something wrong, and we have to abort. And yeah, what can we do if this happens? So one thing you could think of is maybe you just restart the computation. So here in this example, the clients would give their inputs again, the servers do some computation, and then either something else or the same thing could go wrong again. So obviously this doesn't fix it, and restarting again doesn't fix it. So how can we mitigate this problem, which is like natural to the malicious security with abort? One way to handle this is with so-called identifiable abort. So if this case happens, this one honest server here can know that this malicious server at the top caused this fault and abort, and we can identify this. And also here, these clients want to come to the same conclusion, and in a stronger setting, we have publicly identifiable abort. Completely external parties come also to the same conclusion. They find out that this one server was causing this abort. Maybe they can punish them outside of the protocol with some financial penalties or something like that. So this is a nice property. How can we achieve this? So as a base, we use like a maliciously secure protocol with abort without identifiable abort, the so-called speeds protocol, which is relatively efficient, and it can compute arbitrary functions. So whatever we want to compute in MPC, we can do with this. And they use as a base building block so-called secret sharing. So here with the notation, this bracket of x is the share of a value x held by party I. And it's chosen in such a way that if you sum up all these shares, you get back the secret, but the shares on their own don't reveal any information. They look completely random. And also, you need all of the shares together to get to the result. So with this, we can tolerate up to n-1 corrupted parties. And a nice thing of this is that we can still do all the linear operations on it, like adding shares, without any operations or anything special. And then to compute all the functions, we need something like multiplications. And for that, Speeds uses the called offline phase, where we produce correlated shares, specifically some multiplication triples, A, B, and C, where they are completely random under the condition that C is the product of A and B. And then there are efficient protocols how we can use this in combination with the linear secret sharing to also do multiplication. Then how do we add identifiable abort to this? So Speeds already has some kind of verification mechanism. They use some MACs to find out if a shared value is okay or not. And then some later work brought that down to a share level with either MACs or commitments, and then we have for each share of all the parties if they are correct or not, basically. Which nicely gives us identifiable board, because if we know of this specific party, the share is not what we expect, then they probably misbehaved. But what is often not considered is, on the one hand, publicly identifiable abort, and on the other hand, this client-server setting that I had in the example from the beginning. Partially because it's also hard in the way they use these cryptographic protocols in their cryptographic primitives in the protocols, which I will come back to later. But anyway, if we have this verification mechanism with MACs or commitments, they are chosen that they are linear. So in the combination with the linear secret sharing, we can still do all the linear operations like in Speeds. And then the offline phase is also just, we have to now generate these MACs or commitments on the correlated shares like these beaver triples, and then we can do all the computations in a very similar way to Speeds. And yeah, with just basic authenticated shares, like without any correlation, we can build these more complex things like beaver triples in a very similar way. So that's usually not a challenge. There are well-known techniques for that. And then back to the identifiable board, the concrete techniques is on the one hand MAC-based things, and on the other hand things that use public key things like commitments or homomorphic encryption. In the prior work, these MACs are usually pairwise between all parties. So if a party has their share xi, all the other parties have a MAC on this share, and all the parties have their own MAC keys and so on to verify this, because it's like a symmetric primitive. The MAC itself is very simple. You have this MAC key alpha that you multiply with the share, and you add some randomness to it. On the other hand, the linear thing, the public key things are usually just commitments like Pedersen commitments or lattice-based commitments. And then the MACs are very cheap to compute. Because of this pairwise structure, you only have peer-to-peer communication, no broadcasts, which is nice for concrete efficiency. But all the protocols that we looked at had like an extra overhead factor, at least n, so the number of parties, at least in the offline phase. Yeah, basically due to this pairwise nature, and it's also somehow unclear how we can extend this to easily do this client-server setting. Do we have then to all the clients, do they have their own MACs on this, or do we give the clients the MACs that the parties already have, but if they then collude, do we find out some secret information? So this is not too straightforward. On the other hand, if you have the public key primitives, then this publicly identifiable board is easy. Everyone can just verify commitments, and in the same way, if the clients get some shares back, they can just check if the commitments are what they expect. So we also get that very intuitively. And also the asymptotic complexity doesn't have this extra factor of n. It's all good. On the other hand, we have a lot of broadcast communication of these big commitments. We have extra zero-knowledge proofs. And also the compute load to compute these commitments and verify all them is much higher than for these MACs. So what we do is we use some kind of global MAC instead of a pairwise MAC, which gives advantages of both methods. So we have just one thing to verify, it's lightweight, and also naturally goes to the client-server and publicly identifiable board settings. So this is how the MAC that we use looks like. It's, again, some MAC key that we multiply with the shares, and the randomness here comes from some PRF. And to verify it, we just basically recompute it, and we can do still linear operations on it. And yeah, it's a well-known MAC, and also some of these pairwise constructions use exactly this MAC, but just in a pairwise way. So how can we now use this as a global MAC? Because the problem is we don't want any single party to know the MAC key or the PRF. Otherwise, they could forge anything that they would want. So what we do is we take inspiration a bit conceptually from this pairwise approach, but now we interpret all these pairwise MAC keys basically as shares of the global MAC key, and we define our global PRF as just the sum of these n PRFs. So we can have each of the compute parties just compute their pairwise MAC basically. Then one problem is how can we compute this without leaking the individual shares. For example, here this xi belongs only to party I and no other party should know it, otherwise the privacy breaks. And we solve this with homomorphic encryption. So party pi encrypts their shares, the other can use homomorphic encryption to multiply their MAC key on it, and then they can evaluate the PRF, encrypt it, and add it on top. And this drowning encryption is just to hide this extra information about multiplying the MAC key. Yeah, so this is all good, but how do we then verify this? So in a normal MAC check, if we have the key and we have the PRF key, then this is very straightforward. And this is also what we opt for. So everyone can very easily check MAC tags. But the other thing that we need to check is that the MAC tags were also correctly computed, because otherwise we don't know if the MAC check fails because the party misbehaved in computing the attack or others did something faulty when they were together with homomorphic encryption, giving them their MAC tags. So the nice thing here in this construction is if we already have the global MAC key public, revealing these MAC key shares doesn't reveal any extra information. And in the same way, these partial PRF keys. So we can also just publish these in addition. And then we can basically just recompute this equation at the bottom for the homomorphic encryption. So what is missing here is the randomness used for the homomorphic encryption, but that is also only used to hide multiplying this MAC key share and hiding this PRF. So if we also reveal this, it's fine, because at the verification time, the other things are also known. So with this, only we need to basically communicate 3 extra elements, and we can verify all the MACs and the MAC tag generation. So the protocol basically works like this. We first generate the the keys, then we do an offline phase where we generate tagged random values. We use them in an online phase, very similar to speeds. Here everything is also tagged, and then we publish the MAC keys. Then we first verify the online phase. If all the ciphertexts were computed correctly, then we verify so first offline phase, then the online phase where we check the MACs, and then we go to the outputs, which we previously didn't reveal because otherwise we might leak intermediate values. So how do we check these? Because we should check these as well. And we basically follow the same principle and tag them, but now with a different MAC key because we already revealed the MAC key, so we cannot use it again. So we basically just do the same thing again. We verify the offline phase and then the online phase. So the main overhead from this whole construction comes from verifying this homomorphic encryption. So we implemented it and saw that like even on a laptop, it's relatively low overhead per encrypted element. And if you assume these servers have good hardware because we want to outsource them in the first place, then it goes down to like a few nanoseconds per element that you want to verify. And the MAC tags, checking that is like 2 orders of magnitude less, so that's something the clients can easily do. And here again, if the clients have better hardware, also again, 2 orders of magnitude between the hardware. If we look at it, how that performs for just multiplications in the online phase, we have like this factor 4 in a fast network and factor 2 overhead in a slow network for our protocol. And this approach is like this overhead of factor 2 in communication that we have because we additionally publish all these tags. So if, with enough compute, basically we're going to this communication overhead. Then another use case we looked at was federated learning with secure aggregation. Here we have some multiple parties that will later be our clients that want to train a machine learning model together. They have some private data, but the same public model. They locally train it, and then they want to aggregate their model. For this, they can use MPC. So they send their model to MPC servers, they do the aggregation, and send the updated model back to the clients. Then they can repeat this as often as they want. And here, it's good to have this publicly identifiable board so the clients can see if this computation failed, why it failed, and which servers to blame, maybe use other servers in the future. And also, the input to the MPC and the output from the MPC is like the biggest part of this computation because the aggregation itself is not the big part. So this should be also very efficient. We benchmarked this use case as well. Here in the online phase, we are a bit slower than speeds in the fast network, but even faster than speeds in a slower network, and this is because we don't need any extra information for the clients to verify what they get, because they can directly verify everything based on our publicly identifiable scheme. And you nicely see that in the offline phase, where Speeds has to generate like a lot more information, so Speeds has a factor of 2 overhead without getting any identifiable board compared to our protocol in this use case. So overall, we are the first to introduce a protocol that uses this kind of global MAC on individual shares to get publicly identifiable board and work nicely in this client-server computations. The asymptotic complexity is the same as if you use some homomorphic encryption-based speeds, and also the concrete overhead is like this bit of compute and factor 2 in the online phase, roughly, for multiplications. And we think it's very nice to use this protocol for outsourced computations because you get these additional benefits. Here are the references, and thank you very much.
Thanks for the presentation. I think the first question goes to Nigel.
Hi, thanks for your talk, very good. I understand that this is not reactive, so you have to open all the Macs at the end, so you can't open something and then continue, open something, check the Macs, then continue. Mm-hmm. Is that right?
Yeah, I mean, I thought about this a bit. It's not in the papers, but it was like in some draft of the papers. You could basically, this two-phase approach that we have here with the outputs, you could generalize it and have like a Mac after every phase and then do reactive like that, basically.
But then you'd have to remap everything from the first phase, yeah?
Yeah, I mean, you basically the switch to the output is like a remacking, and then you have like this.
You'd have to remap the entire state.
No, you have to remac only the things that transition the states. Yeah, if it's,
which is the state, which
yeah,
could be huge, yeah?
It depends on what you do.
Okay.
Are there more questions? If not, then let's continue to the second speaker. Thanks again, Mark. And the second speaker is Luisa Siniscalci, and she's going to talk about round optimal black box MPC from polynomial time assumptions.
Hi. Thanks for the introduction. There should appear some slides. Okay. So this talk is about MPC. So we already had the general introduction about MPC. The idea is that there is a set of parties that they want to compute a common function. They have their private input. And now the security of MPC tell us that the only things that the party reveal is the output as long as the function allows. So what is the setting that we are interested in this talk? So we are in the plain model, which means no heuristic assumption, no setup. We are in the dishonest majority setting, which means that n-1 party can be corrupted. So at this point, the best security, one of the best security that we can hope for is unanimous abort. And we require that the simulator has only black box access to the adversary. So which means that there is black box simulation. Okay? So that's the setting that we are interested in. And what are the questions that we are interested in this setting is what is the round complexity of those protocols? What is the minimal set of round necessary to construct this protocol? Why round complexity matters? Well, because it's a matrix of efficiency, in particular in very high latency network. It means how much time the party needs to be online, which increases if the network of the latency is very high. So we want to minimize this round complexity. So let's look a bit at the state of the art of those protocols. So the optimal round complexity of those protocols is 4. So there is a lower bound that tells us that at least 4 rounds are necessary for those protocols. And there is a set of works that lead to show what is an upper bound to those protocols using just oblivious transfer. So, but those protocols make non-black box use of the underlying primitives, which means that the primitives are not used in a black box way, So you kind of look inside the primitive on how it is constructed to build your protocol. While we would like to rely on the use of the primitive in a black box way, which means that I am just going to use the input-output behavior of this primitive. Why this is important? Well, this is very important for efficiency reasons. Although the protocol that I am presenting here is not concrete efficiency in any meaning, but the technique used usually for, in the case of black box use of primitives leads to very efficient, are techniques that then are used also for efficient protocols in practice, okay? So what is the scenario when we want to use black box use of primitives? Okay, so there was a work by Shai et al. That constructed a 5-round protocol. So one more round with respect to optimal. Then there was a subsequent work that matched the lower bound, but using sub-exponential assumption. And further, there was a work by Champi et al. That instead matched the lower bound, used polynomial time assumption, but just for a restricted class of functionalities. So the very natural question here, can we close this gap? Okay? So the answer is yes. That's why I'm giving the talk. And in the rest of the talk, I am going to show what was the technique previously used and how we overcome the main bottleneck. So the main technique used in all this type of work was so-called the IPS compiler. What is the general idea of the IPS compiler is to have two MPC protocols which have weaker security guarantee and combine it in a one that has stronger security guarantee. So the first protocol that we are using is called the outer protocol. In this setting, there is N client and M servers, and it's a 2-round protocol in which in the first round, the client secret share the input, and then they are going to retrieve the output from the message of the servers. And what is the security of this protocol? This protocol is secured with selective abort and with active security, but just when a fraction of the server is corrupted. A tiny fraction of the server is corrupted. So what is the second ingredient? Well, it's the inner protocol. The inner protocol is secure against N-1 corruption, but only with the semi-honest security. So what is the idea to combine this protocol is to let the party using the inner protocol to emulate the computation of the server. So, but now the security of the semi-honest protocol is just semi-honest, but the adversary is actually active secure. So he can just misbehave until the composition as it is now, he can just misbehave in all the execution of the protocol. So we need an additional mechanism, which is called watch list. What is the idea here is that we let the party check some of the protocol execution. Since the input is secret shared, this is completely safe, so we are going to check that some of the execution are consistent. And we are going to check in such a way that the adversary doesn't know which of the execution I am going to check of the inner protocol. So this ensures that if the adversary does not want to be caught, and we can just abort since we are in the unanimous abort scenario, he can cheat only in very few instances. And since he can cheat only in very few instances, then we can rely on the security of the outer protocol to claim that the entire MPC protocol is secure. Okay? So that's the general idea of the IPS compiler. Now, how are we going to shrink it in just 4 rounds? So the work of Shai et al. To do this compressing started to require a bit more from the inner protocol. In particular, the first 2 rounds of the inner protocol, the adversary can misbehave arbitrarily, and we are still ensured that the inputs of the party are not leaked. Okay? So we are requiring a bit more than semi-honest from the inner protocol. which allow to compute, to run in parallel the last 2 rounds of the watch list protocol and the first 2 rounds of the inner protocol. Okay? So because the inner protocol has this additional guarantee and the watch list has 4 rounds, I can check consistency in the end of the 4th round and only complete at that point the 4th round of the inner protocol, which is just semi-honest secure. Okay? So that's the approach of Ishai et al. What is the main bottleneck here? Where that this watch list protocol is our parallel execution of simulatable secure OT, which requires at least 4 rounds by the lower bound that we saw before, because it also applies to oblivious transfer. So how we can overcome this gap? Well, the work of Champi et al. Gave a relaxation of the notion of watch list. It says, OK, this watch list is, we cannot achieve the same level of security. Let's aim for a weaker notion of security. And the security that we are focusing here is so-called sometimes aborting adversary, which means that if the adversary aborts in the 3rd round, then we are not going to claim any security. But if the adversary runs the 3rd round of the protocol, then we can claim simulation-based security of the watch list protocol. Okay? That's why, so if we are executing now the watch list protocol and the inner protocol, with this particular property of that the first 2 rounds of the inner protocol you can misbehave arbitrarily, then you have a protocol, you have a 4-round MPC protocol which is secure against sometimes aborting adversary. In particular, because the adversary can decide to abort or not in the 3rd round. If it aborts, then there is no security. But if it does not abort, we can claim normal simulation-based security. Okay? So that's the approach of Champi et al. What goes wrong when we want to claim full security? Well, in the 2nd round of the inner protocol, I am already using the inputs of the party, which means that if the adversary decides to abort in the 3rd round, then also the inputs of the party is leaked. Okay? So that's why they cannot do general functionality in this case. So that's what we focus on in this work, and we try to overcome this problem. How we are going to overcome this problem? So we worked with the inner protocol, dividing it a bit more. Okay? So now the inner protocol has 2 parts. One part does not contain the input, and the second part, and only the second part contains the input. So only the orange and green messages contain the input of the party, while the black messages don't contain the input of the party. You can think about that the black party establishes some correlated randomness, then is used in the colored messages. Okay? So at this point, I can check consistency of the established correlated randomness to claim then that the adversary if he behaved consistent, nothing on the input of the party is revealed. Okay? So we have still this form of semi-malicious security. Okay? So now if we plug this with the watchlist protocol, well, we didn't achieve much so far, because the inputs of the party is still leaked by the orange messages. So we need to protect these orange messages in some way. So let's say that I have a safe for now. Okay? And if in the end of the 2nd round, I am going to put the orange messages in a safe, and I am going to send this message in the 3rd round, then in the end of the 3rd round, I will know if the adversary aborted or not. If he didn't abort, well, I am safe, right? Watchlist security actually works. And so at this point, I can reveal the 3rd round message. So a caveat here is that now I already burned 3 rounds of my protocol. So I have just 1 more round, and that's it. So this safe has to do more. It does not only reveal the message, but also I need a way to compute the 4th round messages of the protocol, which is the 3rd round of the inner protocol. Okay? So I want something more from this safe. And so I want a safe that unlocks and also enable me to compute 1 more round of the computation. How I am going to do that? Well, using garbled circuit. Okay? So the input of the garbled circuit is the 2nd round of the inner protocol, just for the messages regarding the input of the inner protocol. And the 4th round that the garbled circuit is going to output is the 3rd round message of the inner protocol. Okay? So so now the crook is how to communicate labels to the parties. So, and to do that, we are gonna use oblivious transfer. So, what is the input of the oblivious transfer is the 2nd round message of the inner protocol. And based on the labels, I am based on this second message of the inner protocol. Through TOT, I can basically have the correct labels and evaluate the garbled circuit safely. So what is the idea here is that in the 3rd round, we are executing this 3rd round of the oblivious transfer. And at this point, I can claim security that this message is protected because I am invoking the security of the OT. If the 3rd message passed and there is no abort, then I can rely on the watchlist protocol to finish the computation. If if the adversary is aborting in the 3rd round, then I can invoke the security of the OT. So that's a very high level how we solve this problem. Some subtleties, well, the adversary can just choose different messages in various invocations of the oblivious transfer, because now I am showing the protocol for 2 parties. But actually, here we are in the multi-party setting, so the adversary is playing multiple OTs, and he can just choose his different different 3rd round messages, different orange message. Okay? So we have a way in the paper to deal with this problem. And one additional very important observation is that here we are garbling an X message function. But we want to also be black box in the use of the primitive, so which means that we can garble this function only if it does make any use of cryptography. And so we make sure that we use an inner protocol that has these additional characteristics. So this concludes the talk. And to conclude, we gave the first MPC protocol that make black box use of the underlying primitives in the plain model, assuming polynomial time assumption for any functionality. Interesting open problems are, we are making, in our protocol, we are making black box use of semi-malicious OT, which is more than semi-honest, so it remains open for semi-honest, or to use a 4-round fully simulated, 4-round malicious OT, fully simulatable. And the protocol that I described works for unanimous abort. It doesn't work as it is for identifiable abort, which is an interesting direction. That's all. Thank you.
Thank you, Luisa. Are there questions from the audience? So you said that you have to be careful with the labels, so there's no leakage, some selective failure, this kind of stuff. How do you actually make sure that the garbling is correct without throwing NISIX on top and being black box?
So there is no you don't need to, it's okay even if the garble is not correct, because then you can rely just on the security of the underlying protocol, that at that point is active secure. So if I don't garble the correct function, I am going to retrieve a 3rd round of the inner protocol that is not correctly computed, which in the end is just a reduction to the security of the inner protocol that has, where the adversary can actually misbehave in the third round. So you don't need to check the consistency of the garbled circuit.
Okay, thank you. Let's thank the speaker again. And the last talk of the session is going to be by Yizhu Yao, who's going to talk about efficient PCGs for any finite field.
Okay, thanks for the introduction. I am Yizhu Yao from Shanghai Jiao Tong University, and I'm going to present our work, Efficient Random Correlation Generator for Any Finite Field, which has joint work with Zheli, Chaobiqing, and Chen Yuan. So typically, modern MPC protocols features an offline-online design in which the parties first engaged in a setup protocol, which is often cryptographic, and generates correlated randomness, which are typically the biochippers. And then, with the correlated randomness in the offline phase, when the inputs come in, this correlated randomness can be consumed to compute the output of the function fxy efficiently. And the online protocol is usually information theoretic and fast. However, while the online protocol is practically efficient, nowadays we can see these improvements, but the offline phase usually dominates the overall cost. And so there is a major goal is to make the pre-processing cheaper. That's what we do. To solve this issue, a seminal work of BCG IKS19 proposed a beautiful framework of the PCG paradigm, where the expensive setup protocol is substituted by a cheap setup protocol, where it generates correlated short seeds to the parties. Then, with the seeds, each party can expand locally and silently from the seed to the desired long such random correlations, then which can be used to the online phase protocol. So this significantly improves the overall complexity, since the setup protocol is usually polylogarithm in the length of the circuit size. Now let's first review the current landscape of the such random correlation generators. Here we focus basic and very useful primitive, the oblivious linear function evaluation, where each party is given a random value and additive sharing of the products. Before our work, I first want to mention that OLE is a two-party primitive, and what we want is a multi-party pivot triple. So a key fact is that with a so-called programmability and OLE, for a PCG for OLE, we can directly get a multi-party pivot triple by a standard transformation. So parallel to our work, previous work either require a quadratic computation in the length of the number of OLE, or have undesired restriction on the field size, which is we want to mention that the BCCD23 works for almost finite fields, but fields in the most significant case, that is the binary field case. And in this work, we break the field size barrier of the previous works while maintaining the fast computation and opening programmability. We then evaluate our construction based on the source code of foliage, and on generating multi-party chippers, we can generate them in sublinear communication and avoid the broadcast channel used in the foliage paper, which incurs linear communication. As a downside, our city expansion time is almost twice as slowly as the foliage. In addition, our work can generate authenticated binary chippers in the two-party settings in sublinear communication. Well, compared to previous work on large fields, our work achieves chip generation speed 43,000 per second. And in particular, I would mention that this is the first time a sublinear PCG can generate authenticated binary triple. Now let's dive into the technical details. First, let's review the PCG paradigm from ring LPN in BCG IKS 20 paper. First, the parties are given two sparse elements from a polynomial ring over the field Fp and a seed. By the ring LPN assumption, the parties will get a random element over Fp, B0 and B1, which is computationally indistinguishable from uniform. Since S0, E0, S1, E1 are sparse elements, this additive secret sharing of can be succinctly shared by distributed Pulling functions. And I would like to say that what we want is to compute the additive secret sharing of B0 and B1. And by the equations that we know that it subject to additive secret sharing these 4 terms, and we use DPF. This actually gives an ORE correlation over the polynomial ring of Fp. However, we want ORE correlations over Fp. And to this end, it is required that the polynomial ring Fx to the power of n-1 is fully reducible over Fp, so that it can be turned into an ORE correlations over Fp via the Chinese remainder theorem. However, this comes with a limitation that P must be larger than N. A follow-up work of BCCD 23 solved significantly mitigate this issue by introducing a multivariate of the polynomial ring and basing on their security on the so-called quasi-abelian single decoding problem. And now it suffices to require the degree of the polynomial D divides P minus 1, so that we still have a Chinese remainder theorem, and this holds. So it turns back to an ORE correlations of LP. However, since since D is at least 2, so we get that P must be larger than 2. So how to solve this issue? In other words, we found that to get an ORE correlations over Fp, if we start an ORE correlation over a polynomial ring of Fp, then we'll be stuck at P must be larger than 2. But instead, we can think of that if we start with an ORE correlation over the polynomial ring over an extension field, then we can get easily pass the restriction, and it is only required that P to the power of k is larger than 2, and we can choose a large k. However, this fails because there is no ring isomorphisms that turns things back to the base field Fp. So so what we do is to build a transform that turns things back to Fp. What we use is a trace function, which is Fp linear and has this form. Now, suppose that the goal is to get an ORE correlation over the extension field with respect to the trace function, and they can locally apply the trace to get the desired ORE correlations of LP. So how to prepare this? We turn back to the polynomial ring. We turn back to the polynomial ring and define a trace function over the polynomial ring, which is almost the same as the trace function over final field. And the goal is to share over the polynomial ring with this form. However, we still need to examine the correctness and the efficiency when plugged into the PCG paradigm. To this end, we characterize 5 properties which is necessary and crucial for the construction. The first 2 properties are used for proving the correctness, and the last 3 are used for efficiency. Now, the most important is the commutative. We have the commutative diagram. That means that applying trace on the polynomial ring is essentially identical to applying trace on the Fp to the power of k. And the second is additive homomorphism. Since we will use distributed point functions which output the additive secret sharing, so we must have 2 these two properties. Regarding on efficiency, we need to require FP linearity property, which is inherited from the trees over F. And one can think of that with this property, trees can be observed in another. And the first property is the sparsity, which means that trees of a sparse element of the polynomial ring has also a sparse characterization. And finally is the extraction, which means that we can establish a one-to-one map from the polynomial ring to an kn length vector space over Fp. So how do we use this? The first is that we have proven the equivalence by the first two properties. Then we use the following, and we can use the proposition 4 to just by calculation, by the definition of the trees function, we want to share the multiplication or additive seek sharing of the two trees function. And just by calculation, we get this, and by proposition 4, we have that we need to share 4 squared cross terms, which are of t squared sparse. Then recall that we can absorb one trace in another, so the cross terms are significantly reduced by a factor of k. So there are 4 k cross terms needed to be shared by the DPF, and we will get NOR correlations over LP. And finally, by the extraction property, the cross terms can be reused to extraction more in total kn OR correlations. Just they are uniform, and we have this. You can check this offline. Now let's see a concrete example of our instantiation from F4 to F2 ORs by the trace. Here we are some QSD over F4, and we have this equation. One can also check by online, offline. And there are 8 cross terms which are of t squared sparse, and we can produce 2 NOR correlations. Yes. And finally, I want to introduce an application of our PCG, which can produce authenticated binary retrievers in the two-party setting. The different things is that we need to share a term with the MAC key, MAC key delta, which is taken from an extension field of LP to the power of lambda. However, our assumptions are over F4, and the trees are defined also over F4. We found that, fortunately, this will be not be an issue, as long as we require the F2 to the lambda is an extension field F4. But unfortunately, there is one property that we cannot apply applicable because the F2 linearity, because this delta belongs to F2 to the lambda, which is the extension field. And finally, we by sharing 16 cross terms, we can get to an authenticated binary retrievers by proposition 5. Now, in summary, in this work, we construct efficient PCG for many useful correlations. This include OLE and beaver triple in the multi-party setting, and two-party authenticated beaver triples. There are also matrix multiplication triples and string OT, which are omitted in this talk. And also, our PCG are as efficient as previous PCG for large fields, in the same sense that we achieved almost the same communication, and the computation is almost twice larger. Moreover, our security relies on standard existing assumptions, such as QSD and real LPN used in previous works. And lastly, I want to say one can think of generate the PCG paradigm to produce more correlations, such as OLE over C2 to the K, or extending to generate more complex correlations of, or just extend the number of tend to generate multi-party authenticated triples. And in particular, the first problem we actually solved and is going to appear at Eurocrypt, going to appear at the crypto this year. Thanks for the listening.
Thank you for the interesting talk, Yeju, and for the great result. And congratulations on the crypto paper. Are there questions from the audience? No, no. So you mentioned how your work is, of course, better in terms of much lower communication than previous works.
Yes.
Did you include also the communication and some estimate of the computation for computing all these cross terms? Because you need to compute some.
Yeah. We evaluated the concrete efficiency, and it's just 2 twice slow. Because we have 2 times cross terms, so the computation is 2 times. But the communication can be amortized because we can extraction.
So 2 times slower than previous PCG works.
Yeah. Ours
like
is slower. So we suggest that we working for the F2 case best.
Okay.
Yeah, to generate F2.
Okay. If there are no other questions, then let's thanks the speaker and all other speakers from the session again.
Thank you.